This may be climate skeptics' favorite graph, and at first glance, it seems to show that climate change is just a part of Earth's natural cycle. And in some ways, it is. Earth has always warmed and cooled. But according to its natural cycle, we should be in the beginning stages of a gradual cooling trend, eventually leading to another ice age. But we're not.
We've totally broken the ice age cycle, and we're not going back into another ice age.
The reason for this is simple. We've added around 50% more carbon dioxide to the atmosphere than in previous warm periods. But this is where things get confusing. When we look back at Earth's past climate, CO2 doesn't seem to be the thing that kicks off the warming. In fact, temperatures start rising first and carbon dioxide levels follow. Every single time. So does that mean CO2 doesn't actually determine global temperature? And if not, could there be something other than fossil fuels behind global warming today? Let's get to the bottom of it. More than 70% of US citizens today agree that the Earth is warming. And that's not really surprising because the evidence is everywhere. Glaciers and sea ice are disappearing, Antarctica is getting greener, and days of extreme heat have increased dramatically. What fewer people agree on is why. Zeke Housefather is a climate scientist who's frequently in the media, including on this show. He told us the two most common arguments he gets from climate skeptics are: one, the climate has always changed, and two, it's the sun. And the reason these arguments are so compelling is because they're right, or at least kind of right. Let's start with the sun.
So when we talk about solar cycles, there's really two different things we're talking about.
The first is the solar magnetic cycle, where the sun's magnetic poles flip. This 11-year cycle influences solar activity, including sunspots, solar flares, and very slight variations in the sun's energy output. While these fluctuations can cause incredibly minor and short-term climate effects, they don't explain the long-term warming trend that we're currently seeing today. Satellite measurements since the 1970s show that solar energy reaching Earth has actually declined as global temperatures have not only continued to rise, but actually accelerated. So for the sake of this video, we can forget about this first kind of cycle. But the other one is a lot more relevant to this conversation because it's behind the ice ages.
Ice ages for a long time were a big scientific mystery. Earth scientists didn't really understand why they occurred when they did. And it took Milankovitch, who finally proposed that it's actually due to these small changes in the Earth's orbit that happen over periods of 20,000, 40,000, 100,000 years.
And these are three different changes here that combined trigger ice ages by changing the distribution of solar energy across Earth's surface.
The first is what we call precession. So it's a shift in the orientation of the Earth's axis of rotation. So essentially a little bit of a wobble in how the planet rotates. And it affects the amount of summer sun that's received at high latitudes.
Then there's obliquity, which affects the Earth's tilt. As obliquity decreases, we get warmer winters and cooler summers, which allows more snow and ice to build at high latitudes. Then there's the final and most important factor, eccentricity,
which is the shape of the Earth's orbit. So how sort of circular or more oval shaped it is. And that alters the length of the seasons. Precession is on a roughly 26,000 year period. Obliquity is a roughly 41,000 year period. And eccentricity is a roughly 100,000 year period. Combination of those three really has a big effect on the amount of sun reaching the poles and particularly reaching the Arctic.
Arctic ice formation is especially important for ice ages because the northern hemisphere has more land, which is easier to freeze than the ocean. When ice forms, it reflects the sun's radiation back into space, which cools the Earth and leads to even more ice formation. This creates a feedback loop, and eventually Earth enters an ice age. But as Milankovitch cycles continue, Earth shifts its relationship to the sun. The Arctic then receives more sunlight and melts enough of the ice over a long period of time to bring us back out of an ice age. This theory is now widely accepted as the impulse that begins or ends ice ages. So yes, sun cycles, or at least extremely long orbital cycles, do affect our climate. So how does CO2 fit into this equation? While Milankovitch cycles initiate climate changes, CO2 amplifies their effects by creating a feedback loop. When more ice forms at the poles due to slight changes in Earth's orbit or tilt, more sunlight is reflected and causes more cooling.
That cooling causes reductions in CO2 concentrations because colder ocean water absorbs more CO2. Vegetation is taking up less CO2 because it's covered with ice. And these carbon cycle feedbacks in turn lead to less carbon dioxide in the atmosphere, lead to colder temperatures, and push the Earth further into ice age conditions.
And the opposite is true when we're moving out of ice ages.
Retreat of glaciers, higher vegetative activity, warmer oceans, a bunch of different factors that combined lead to more carbon dioxide in the atmosphere, which itself is a feedback loop leading to more warming.
So Milankovitch cycles initiate warming, warming increases CO2, and CO2 amplifies that initial warming by trapping even more heat.
CO2 is remarkably good at trapping heat in the atmosphere, particularly the heat that re-radiates from the Earth as it's absorbed by the sun, gets blocked by CO2 molecules, re-radiated back down, and it warms up the planet, which is a good thing. If we didn't have CO2 in the atmosphere, the Earth would be an uninhabitable ice ball.
And something like that has actually happened before. During the two theorized snowball Earth periods over 600 million years ago, average global temperatures are believed to have dropped to around -50 degrees Celsius or -58 degrees Fahrenheit. The planet was almost completely frozen, with ice stretching all the way to the equator. It's likely that the Earth was only able to escape these deep freezes thanks to CO2 and other greenhouse gases. Over millions of years, volcanic eruptions gradually released enough greenhouse gases to warm the atmosphere and eventually melt the ice.
The fact that we have greenhouse gases at all is good. It's just you can have too much of a good thing.
Which brings us to today. Since the Industrial Revolution, we've emitted about 1.8 trillion tons from burning fossil fuels, and approximately 1.1 trillion tons of that has accumulated in our atmosphere.
To put that in perspective, that's roughly the equivalent of burning every living thing on Earth, or the mass of everything that humans have ever made. The pyramids, the roads, all our skyscrapers and buildings. We put that much material into the atmosphere.
Which has led to an incredibly dramatic increase in atmospheric CO2. We know that because in 1958, Charles Keeling began measuring it at the Mauna Loa Observatory in Hawaii. This led to the Keeling curve, a daily record of atmospheric CO2 showing levels rising from 315 parts per million to about 420 parts per million. And like I said earlier, that's 50% more than at any point in the last 800,000 years. And we know this because scientists are amazing.
When ice forms in Antarctica, bubbles of air get trapped into the ice. So it's like this time capsule. All you really need to do is go in there and melt the ice and measure the bubbles, and you actually have a sample of ancient atmosphere.
So we can extend far beyond the Keeling curve and compare CO2 today with paleoclimate proxy data from millions of years ago. Maybe even more amazing is that CO2 molecules actually tell us how they were created, either naturally or by the burning of fossil fuels.
The chemistry of the CO2 in the atmosphere that comes from humans is different. It actually has this unique chemical signature of ancient dead carbon. Because we have that chemical fingerprint, we can see that increase in that fingerprint through time, which tells us that the CO2 is going up, and it's also definitely from fossil fuels and not from any other source like volcanoes or anything else.
So we know that CO2 has a powerful warming effect that has led to temperatures rising far above what they would be if we hadn't burned fossil fuels. We've already passed 1.5 degrees Celsius of warming, but how much warmer is it going to get from here?
Right now, 420 parts per million in the atmosphere, right? And we know the ice ages were like 200 to 300. We've totally broken the ice age cycle, and we're not going back into another ice age. And we know that because the last time it was 400 parts per million was a much warmer world 3 million years ago.
And when Jessica says much warmer, she means it. According to her recent study, the estimated temperature during this time, called the Pliocene, was an average of 4.1 degrees above pre-industrial levels, which is almost 3 degrees warmer than today. And beyond this, Jessica's research shows that due to slow feedback processes like the melting of ice sheets and changes in vegetation and ocean circulations, which can take up to millions of years, warming could continue to get worse even if we don't put any more CO2 into the atmosphere at all. The only way to avoid increasingly severe consequences is to stop putting greenhouse gases into the atmosphere, because it stays there for a long, long time.
If I burn a ton of coal, put a ton of CO2 in the atmosphere today, it would take somewhere in the order of 400,000 years for that ton to be fully removed. So the fact that CO2 stays so long in the atmosphere means it can have a really big effect on the climate as a result of our cumulative emissions of it.
But what makes today's climate change particularly alarming is not just how much temperatures are rising, it's how fast it's happening.
One thing we know from the geological record is that rapid climate change is often associated with mass extinctions. I mean, that is fast climate change doing its work and turning over the pool of living things on planet Earth.
We're already experiencing devastating consequences from human-caused climate change. And even though this is fast, we know that the climate has always changed. Can that at least bring us some hope?
Has the climate always changed? Yes, it has. And on the geological timescale, in a big way. We have had long geological times of really, really hot temperatures on planet Earth, and we've also had extremely cold temperatures on planet Earth.
But it's never happened quite like this before.
We're talking about centuries or less. And on that timescale, we don't know of any kind of natural climate change that happens that fast in the deep geological past. So this is really different from the kind of natural climate changes we see.
The fact that the climate has changed so much in the past is not something that should give us comfort, because it means that the climate is fundamentally very sensitive to small changes in the amount of energy that reaches it. And now we're changing the climate in a big way. So the argument that the climate has changed before is more of a reason to worry than a reason to assume that what's happening today is not a problem.
If we're going to continue to thrive on this planet that's experiencing escalating climate and weather impacts, we have to learn and evolve our understanding together. And that means looking at all the evidence and properly interpreting it so we can make informed decisions. But the good news here is that for the first time in human history, we actually have the technology to change our emissions and to stop global warming, and to do it in an equitable way.